So you have to find the part. So for here you can write a dA vapor. dA vapor will be, this is a free particle, huh? An exponential z ft zv ft. And dA metal, you know, is 1 over z 1 minus z some type of the function, we call it gt. Now you remember it was just a function of the t. So I want you go and find for the partition functions for this. We already did it, the partition function for the vapor and partition function for the metal, and you will have the d both. So after that you need to have the equilibrium. What is the condition to have the equilibrium? The condition for the equilibrium is that we have to balance the chemical potential, pressure, and the temperature altogether. So temperature is already fixed, you don't have to be worried about that. We use the same temperature here, T. So we suppose that after some time the system becomes in thermal equilibrium. So T1 is equal to T2. You don't need it. T vapor is T metal. So first. But to make a balance for the chemical potential or pressure, you needed to be a little bit careful. The equation which I want you find for me is that starting from this and from this, you can find the pressure. Huh? You just needed to use the equation for the pressure. Q, L, and D is PV over KT, general. So you can find the pressure from vapor and pressure from the metal and make it P1 equal to the P2. Huh? P gas equal P vapor. This is what I will ask you in the homework. If you just find the partition function, I mean this Z, Ft, and Gt, and find the pressure, you will have a very important equations. This is the equations gives you the pressure. This is the part of our work which is interesting also for the sinus hyperbolic. This is the type of the work which will be interesting for the chemistry people. This is the equation for the pressure of the system of the gas vapor. You never can derive this equation by any other method except the statistical physics. You can measure that, of course. You can make the system and start to measure the pressure, huh? And finally you can fit the pressure with the temperature, huh? I hate this fitting or something like that, but you can do that. I mean, you can measure the pressure, get some point and try to make a graph, huh? Like that. And always you needed to see that how much error you have. But you never can get this equation from experiment. You will find a polynomial or something like that, or logarithm or something like that. This is the exact pressure. This is the exact pressure of the gas vapor system. And I told you, this is the very, this is very important, actually, applications of the grand canonical and so on. So there are many other applications for that. But so far as I want, and my aim was that you be familiar with this ensemble theory, because this is a work which you can do for whole life. Just work on the statistical physics of ensemble. So you can spend whole life to study that. And you'll see that, for example, this system can be used for the human body inside the body. For example, you have a virus and you have a tissue of inside the body. And I remember exactly the problem. One time, the person came to me. He was from the medical engineering, and they were exactly looking for the equation like that. So you can find the pressure inside the body when it's affected by some virus. You know? Just you make it to make a simple model for the virus and simple model for the body. So I mean, this statistical method like that, it will use it for, but mainly it can use for condensed matter. And for nuclear physics, you needed that. So, so by this, because there is another information in this chapter, but I don't go through them, but you don't need it. Like the fluctuations and these things are very advanced actually. So by that, I think, as I promised you that, this chapter finished. So after this chapter, we will going to 3 more chapters to see what we can do. So the important things after this will be, I want to go through the Feynman theory of quantum and sound, quantum statistics. So this is also very interesting, and but we don't go again to the details. So we will create the problem in the applications, like here. You know, I go directly to the application and direction to the equation, which I can get some example from that. But this is a very big subject actually. Quantum information and these things come from here. Entanglement, complexity, computational complexity. This is my activity also. The second thing is that I want to talk about the Bose system, bosonic systems. So this is my interest also. So we will spend maybe 2 lectures like that, and maybe 1 or 2 lectures on the Dirac statistics. And we will end here. Definitely, if you know the statistical boson, and if you know about von Neumann, if you know about the ensemble, so you can say that you have a basic information about the statistical physics. So we can finish that.